All right, let's continue where we left off. We mentioned that in matrix multiplication, every matrix takes the inputs when it is multiplied and then it emits another vector, right? So in a way, it takes the dimensions, the input dimensions, and then merges them, meshes them some way, does something, and this operation, this miss and match and merge and this combination of the elements will be meaningful when we go into deep learning. But eventually, it takes one vector and then gives another vector, right? So let's go ahead and see what's actually happening. So in this animation, let's take one input vector. So let this matrix be our matrix 2 1 1 2, and let our input vector be one of the basic unit vectors, meaning 1 0. So we mentioned that this input vector 1 0 can be represented as a arrow vector as opposed to a data point. And let's plot this 1 0 here. And you would agree with me if I tell you, when I multiply this 1 0 with a 2 by 2 matrix, this 1 0 is going to go to another two-dimensional vector. It's going to take a vector and then give a vector. So if I multiply this, if I do the matrix multiplication, look at the first column, 2 1, with inner product 1 0, I just take the first one, it gives you 2. And I 1 2, the second row, I take the 1 0 inner product. The second one, multiplication with 0, disappears. So I take the 1 times 1 times 0 times 2, it gives 1. So 1 0, you see this green goes to 2 1, right? So if I take another one, 0 1, this red arrow, and when I multiply, I go to something else. So if I take some arbitrary negative 1 2, it goes to some arbitrary vector 0 3. So we just mentioned that all of these vectors after matrix multiplication, you see that they all go to new places. I'm going to use the word transform for this because this matrix has some functionality. It takes the vectors as input and it transforms each and every one of them to their new locations. So let's discuss what happens in this transformation. What function, what information, what is the significance of this transformation? Let's go ahead, instead of dealing with arrows, we argued that our vectors are actually deemed as data points on the space, right? So let's display all of the data points. And when I apply this A matrix to each and every one of the data points, whoops, I lost the animation for a second. So if I multiply each and every one of these data points with this matrix, all of these data points, they will go to their new locations. They will be transformed. And if you just focus your eyes on the vectors, which we covered a second ago, one by one, you see that they all go to their locations. And when you see that all of the data points, they go to some locations. And when you look at the space, like the whole space, and all of the data points go to their own new locations, you kind of see that not only the data points, but actually the space is transformed. So this is important. And when we transform the space, all of the data points, they find their new locations. And there are some locations that actually, some data points, some directions, some points that don't get affected by this. Do you see this? So we will have a name for such vectors, a set of vectors that don't go to anywhere, even though the matrix is warping everyone, transforming everyone to their new locations. There are some vectors that don't get affected by this matrix multiplication. Not yet, but we will have a name for such vectors. So we can, lastly, we discussed that each and every one of these vectors, each and every one of these matrices, they go transform the spaces, warp the space in a way. So the one on the top, it took this unit square and it made a parallelogram from it. The whole space changed. And this other one, 1, 2, 2, 1, that takes this space and swaps it and makes a new shape. So the data points, they go to their new locations. And let's take this vector 1, 2, 2, 4. When it takes the input, it just collapses all of them on a just line. In this example, of course, we're starting from two-dimensional space and ending up in a line, but sometimes it so happens that we can start from a very high-dimensional space and collapse some of them to some lower dimensional space. The question of what determines if this space will extend or flip or, God forbid, collapse, something determines it. And the answer of what determines it actually is hidden in the name. But we'll get to that in a second after we cover matrix multiplication.